Here is a gist. Please open this gist and execute the first 2 cells so that by the time we get to the exercise, the installing software part of it will have been finished. I will do this for you. So here it is. Run it anyway. Think a little bit. It will execute this one. And then can you also execute this, second cell as well, which will download some of the data files. OK. All good? Okay, and the gist should be in the Slack channel as well. So you should be able to click on the link in the Slack channel. OK, so you might wonder at this point, why are we talking about the Lyman forest? This is a cosmology school, right? Why are we talking about neutral hydrogen? Well, so neutral hydrogen is intimately connected with cosmology because it is everywhere in the universe. You could think of the universe as a lot of neutral hydrogen, some other stuff you can't see, and some trace elements, right? We are the trace elements. So neutral hydrogen is everywhere in the universe, and more importantly, it traces the total gravitational potential, right? So by the reason to do cosmology with it is that by measuring the distribution of neutral hydrogen, we are trying to measure the distribution of the total gravitational potential and thus the distribution of dark matter and, of course, neutrinos. This is a somewhat complicated relationship. It's not a relationship that you can describe with an easy linear perturbation theory. It's a relationship that you need to use simulations to compute. Fortunately, the simulations mostly only rely on things that we kind of understand how to do, like gravity, and rely only a small amount on things we do not know how to do, like black hole accretion. Okay? So the Lyman forest is one of the classic cosmological probes. The bad thing about it is that it is practically quite difficult. The good thing about it is that it is, in principle, possible, right? Like there are many problems, but the problems are all solvable problems. So this is another way of looking at this is good because it gives me something to do. Reasons for being interested in Lyman cosmology specifically. So I have here a list, an opinionated list of things that are in the universe. So the universe, of course, is mostly dark energy, then there's a substantial amount of dark matter. However, you cannot see the dark energy in clustering because it doesn't cluster. You can't see the dark matter because it is dark. The only way you can get it is through lensing. And then the next on the list is hydrogen, right? So this is kind of the fundamental reason why it makes sense to look at neutral hydrogen, because the universe is full of it. Okay? And then galaxies are a small fraction of the universe. Other advantages of the forest. So you're looking at a quasar sightline, right? So the scale that you can probe is on order of the scale of the feature that you can see in this sightline, right? So this is actually a fairly small scale comparatively. If you compare it to, for example, galaxies, if you're looking at a galaxy power spectrum, the scale you can probe is the separation between 2 galaxies in your survey, right? So this is generally a somewhat larger scale than the Lyman alpha forest, practically. So specifically, we can measure a single line limited by the thermal Doppler broadening of the line, which we'll come to, which can be around a few kilometers per second across. When converted into megaparsecs, this is scales between about 0.1 h inverse megaparsecs to about 20 inverse h over megaparsecs. So 20 is really the smallest scale that is accessible by any probe at the present day. You might be able to do smaller with 21 centimeters at some point. You might be able to do smaller with some futuristic CMB experiment. But for things that we have right now, the Lyman forest is the smallest scale that we can probe. So that is the reason to do Lyman forest. Yeah.
Okay. I have a question a bit maybe more back into the essence of the Lyman alpha and the hydrogen distribution you were mentioning. How much also plasma enters here, like free electrons? I thought electrons were more a larger percentage, but I'm actually not sure. And if you can give us more an astrophysics perspective.
Oh, you mean like in this?
Yeah, in this scenario.
Yeah, so this is by mass, right?
By mass, okay.
Right, so this is the omegas. right? So the mass of electrons is very small, so it's not much.
Yeah. I'm wondering because in the context of the Sunyaev-Seldovich, you can still use it to trace baryons. And also, I was wondering in the previous slide, I think it was, or next, yeah. Neutral hydrogen traces the total gravitational potential. If you can mention a bit more about that, especially in the feedback context. If you have like feedback, I don't know how the neutral hydrogen redistributes with that.
Yeah. So your second question, I'm going to talk about a lot more later. Okay. So it's mostly traces that all of these statements, when I say neutral hydrogen density traces total gravitational potential, implicitly what I'm really saying is the neutral hydrogen density somewhat traces more or less the total gravitational potential with a few caveats, right? And I'm going to talk about the caveats. And the reason that you need simulations is because you need to simulate the extent to which the hydrogen does not trace the gravitational potential. If it really exactly traced the gravitational potential, this would be easy. You would just compute a 3D matter power spectrum, and then you just multiply it by some parameter, and boom, you've got it. You've solved cosmology, right? So it's not exactly tracing it, but it's tracing it enough that you can get cosmology out of it. Your first question was about Sunyaev-Seldovich. So yes, Sunyaev-Seldovich is excellent. It is, of course, a wonderful probe of cosmology. It is the advantage of Lyman alpha is that you are able to probe large spatial regions, right? The Sunyaev-Seldovich effect really only probes inside of clusters. And we'll see why that's important later. The advantage of the Sunyaev-Seldovich effect, of course, is that it probes inside of clusters. So if you're interested in something that happens inside of clusters, like, I don't know, maybe you're interested in like self-interacting dark matter cross-sections, that's going to be pretty useful to look inside a cluster, right? So they have complementary and different uses. You can invite me back next year to talk about Sunyaev-Seldovich effect if you want, or you can invite someone else. But the forest. Okay, so the great thing about the forest is it probes small scales. So here is a slide of all the probes of cosmology that we have. Obviously on the large scales, it's the CMB. This is the matter power spectrum as measured by different probes. Here is weak lensing, and then here is the laminar forest in purple. And you can see that the forest is probing the smaller scales down here. And this is the regime. This line here is more or less the larger scale probed by Lyman alpha, and then it goes all the way around to KF4. Yeah, okay. So first thing to note is that this is the nonlinear regime, right? So we do need, this dotted line is the nonlinear power spectrum. This solid line is the linear power spectrum. Because this is in the nonlinear regime, we do need simulations, right? We fundamentally can't do this without simulation because we need to model the gravitational clustering. And the only way to model the gravitational clustering on the nonlinear regime is to have an n-body simulation, right? And even people who do the laminar forest with perturbation theory, the perturbation theory is calibrated with a simulation at some level, okay? That's the first thing. The second thing is, yesterday I talked a lot about neutrinos. So it will not surprise you to learn that neutrinos are measured by these scales, and so the laminar forest measures neutrinos. So okay, so this gray band shows the scales that the laminar forest is roughly sensitive to. I'm dropping off at 4 here rather than 20 because this is actually EBOS laminar forest, not the smaller scales, not an arbitrary laminar forest experiment. This is the EBOS laminar forest experiment, and that is sensitive down to KF4, which is why this gray band stops here. The effect of neutrino mass, as we saw yesterday, was that it reduces the power on small scales. These scales happen to be exactly the scales that are measured by the laminar alpha forest. So the naive, somehow the naive best way to measure the neutrino mass is to measure the clustering of matter on these small scales with the forest and measure the clustering of matter on large scales with like the CMB or something and compare them and say, oh, look, the forest has suppressed, the neutrino has suppressed forest power by like 10%. That's a neutrino mass, right? That is kind of what we want to do. Yeah. It is hard to do, but that's what we want to do.
I've always been curious why on the previous slide do the Lyman alpha data points not trace the nonlinear expectation?
Oh, yeah, because the way, because they have inverted they've tried to get the linear theory
Right.
power
Okay.
alpha, basically,
Okay.
yeah. It's a, it turns out, I'll talk about this a bit more, but it turns out that it's just as difficult to go from the Lyman alpha forest observable to the nonlinear matter power spectrum as it is to go from the Lyman alpha forest observable to the linear power spectrum. Right, so you take an observable, you invert the data analysis to get out a linear theory power spectrum at like redshift of 100, and then you evolve it forward to redshift of 0, and you get a linear theory prediction at redshift 0. So it's not, this is not like a crucial factor of the analysis. It's just what they happen to do for that paper, would be my answer. Okay. Right, so one thing that I want to say, and which is the point of this paper here, is that you actually don't explicitly need neutrinos in your simulation, right? So if you are doing a Lyman alpha forest experiment, you might think, oh, I need to run a simulation with the neutrino simulation techniques we talked about yesterday in. You actually don't need to do that. And the reason for that is that on these scales, the effect of the neutrinos is just to change the amplitude of structure, right? So you can change sigma rate in your initial conditions, and you can rescale a little bit, and that will get exactly the same answer as if you'd run a simulation with massive neutrinos in explicitly, because we're only probing scales on which they are already free streaming, right? So remember yesterday, I had this explanation of the simplest possible neutrino simulation, where you just say, okay, reduce the structuring, reduce the clustering of structure, and just go for it. And that is more or less what we're doing here. And that works really well because the scales are so small that we do not free stream, right? You have to do a little bit of rescaling, but you can do that in post-processing, okay? So I hope you don't feel, like I cheated you too much yesterday by talking about the neutrino simulation techniques and then not using them. Okay, one thing that you do need, so you do need a bright backlight, right? So you're looking at absorption lines in spectra. To get absorption lines, you need a background source that is bright enough that you can measure the spectrum to high precision, to high signal noise. This is generally a quasar. Quasars are very bright. They exist at very high redshift. They have very long spectra going deep into the UV. And you can take this spectra up to like redshift of 7. There aren't many quasars at redshift 7, but there are some, right? So there are reasonable statistics for quasars, for backlights, for a very wide redshift range. So the range in which we measure the Lyman alpha forest is between redshift 1.8 and 5.4. This is a little bit unusual because normally I don't say you can only measure this above redshift 1.8, right? Normally things at lower redshift are easier to measure. So does anyone want to guess why this range goes from 1.8 to 5.4 and not, for example, 0.1 to 5.4? Any guesses? I'm going to tell you in like 2 minutes. Yeah. Aha, that's a good guess. That's not the right guess, but it's a good guess, right? So the guess is, do quasars drop off at very low redshift, right? And they do, and that would be an issue, but that's not the reason. But that's a good guess.
Thanks. Is it that the quasar emission, that's the backlight, has redshifted out of the range of the line features that you're looking for?
That's closer, right? So the reason is, at redshift less than 1.8, the Lyman alpha line, which is in the UV, has not redshifted into the visible, right? So it is blocked by the atmosphere. So you are looking at your quasar spectrum, and there's like some redshift range that you cannot access, and that's less than redshift 1.8. You can get lower redshift Lyman alpha forest if you are in space. So if you have access to if you had access to a dedicated Hubble Space Telescope, you could do a whole Lyman alpha forest survey at like redshift 1 if you wanted. We don't have that. It would be nice, but we don't have it. I can dream. Why do we stop at redshift 5.4? Right? So I said quasars exist up to redshift 7. It's not just statistics. There's a reason why we can't get the forest at redshift higher than about redshift 5-ish. Anyone want to make a guess? Yeah, go at the back. Reionization, that is the right answer. Yes, reionization, right? So if the universe has not been reionized, then the sightline to the quasar is completely absorbed. You just get a Gunn-Peterson trough, a neutral universe, and it looks kind of like this. This is a stack of real quasars, and you're not going to get any cosmological information if there's no transmission, right? There's no absorption features. There's just a big dark gap, right? And there is information about reionization from that dark gap, but there is no information about the clustering of matter anymore. So this brings us to an important point about the forest. We are only sensitive to neutral hydrogen, right? This NH is really NHI. We are sensitive to neutral hydrogen only. The neutral fraction in the universe at redshift like 3-ish is about 10 to the minus 6. This is important. Lyman alpha is a very strong transition. If the universe were anywhere near completely neutral, this transition would be complete. This sight line would be completely saturated. You would see F of 0 all the way along. This is the Gunn-Peterson trough from the seminal 1960s paper of Gunn and Peterson. Do not forget that Gunn and Peterson were both graduate students at the time when they wrote this paper. So let this be an inspiration to you that if you feel like being one half of Gunn and Peterson and writing a paper like that, discovering the Gunn-Peterson trough, you should do it. Do not be put off by being a grad student. You know, it can happen. I taught Mingfeng this for like 4 years, but he just kept writing papers with me, so that's actually okay. I think someone asked like the UC tenure committee once, if our grad students write papers together and we're not on it, and they turn out to be Gunn and Peterson, does it still count for our tenure case? And the answer is no, which I think is unfair, because I think that having Gunn and Peterson in your group should be worthy of something. Anyway, so this is a Gunn-Peterson trough. Right, so we are sensitive to neutral hydrogen, and we are tracing the dark matter. And we're tracing dark matter on very small scales. But this is actually a little bit better than that. The Lyman alpha forest is not measuring the total matter power spectrum. The Lyman alpha forest is measuring a filtered version of the matter power spectrum. So why is this important? This comes back to the questions about baryons that people have been asking for the last couple of days, right? So I want you to imagine the halo model, right? So the halo model is this classical model for understanding how things cluster in the universe. It divides matter clustering into 2 components, the 2 halo term and the 1 halo term. The 2 halo term is the correlation between 2 halos, right? So the idea here is that on scales larger than the virial radius of a galaxy, the matter clustering is dominated by, if I have one galaxy, what is the probability that there's another galaxy within this range? The 1 halo term is the correlation of matter inside a halo. So on scales smaller than the virial radius of a halo, working out what the matter power spectrum is involves looking at how the matter is distributed inside the halo itself. At redshift 0, the total matter power spectra greater than around like 1 megaparsec, 1 inverse megaparsec to within the order of magnitude is dominated by the 1 halo term, right? So this is why we care about baryonic feedback, right? Because we are dominated by the 1 halo term on really small scales to within an order of magnitude, we have to care about what happens to the internal density profile of large halos. So imagine I have a large galaxy cluster, it's like a megaparsec across, and I have a whole bunch of huge AGN pushing the gas outside of the halo, right? This will change the internal density distribution of the galaxy cluster. So for example, here I have schematically a galaxy cluster without an AGN in, and you can see that the matter is clustering like right in the middle, it's some NFW profile. I have a whole bunch of AGN feedback, it knocks out the gas. The gas is like 10% of the galaxy cluster, right? Because omega B is 0.05, omega cold dark matter is like 0.25, that's like 10%. So if 10% of the gas has been completely ejected from the cluster by AGN feedback, this is going to reduce the density in the central regions. We're going to get a galaxy cluster that looks like this, right? So the halos will be smoothed out, right? So what does this look like in Fourier space? This looks like the suppression due to baryonic physics, due to AGN feedback on the matter power spectrum. So if you're looking at a matter power spectrum suppression due to AGN feedback, this is what it is, right? This is why the baryonification recipes work. They, by hand, remove the gas from the galaxy clusters, and that suppresses the matter power spectrum. And that is because if you are looking at the total matter power, it is sensitive to the 1 halo term on small scales, right? Make sense? Right? So this is a problem for cosmology because we have to understand AGN feedback to do our job. We don't understand AGN feedback. But The advantage of the Lyman alpha forest is that this problem is not solved, but it is less severe than it is for other probes. So why is that? So imagine, so I just told you that the universe is very highly ionized, and a completely saturated part of the universe, a neutral part of the universe is completely saturated and looks something like this, right? So what does the inside of a galaxy look like if you pass a sightline through it? A galaxy has a lot of neutral gas in, right? So what does it look like? It's completely saturated, right? So imagine here, right? Here I have a sightline. This is the gas density in the universe. And here, the sightline goes through a large galaxy cluster, right here. And what does it look like in absorption? Right here, it's completely saturated, right? So why does this matter? If I were to take this galaxy cluster and move the gas around inside it, this will not change the Lyman alpha forest at all, right? Because it is already completely saturated, right? So maybe the optical depth will go from like 10 to the 6 to 10 to the 5. Oh no, but that doesn't matter because both of those are completely saturated. Like both of those, you get no transmission. So there is no information coming from inside the galactic halos in the Lyman alpha forest, right? The Lyman alpha forest is probing this filtered matter distribution with an overdensity between about 10 and about 100. Above 100, you are saturated. Below 10, then there's no absorption at all, so you don't measure anything. And for this reason, what you are measuring is more sensitive to the cosmological information and less sensitive to the AGM feedback, okay? So this is the hidden superpower of the Lyman alpha forest. Yeah, and so here is a real spectrum from Max Bettini's lecture notes going through a small galaxy. So this is a damped Lyman alpha system. And you can see, boom, it's saturated here. We don't care what goes on in there. And then there's Lyman alpha forest outside of it, okay? You do, of course, have to detect when this is happening and remove it from your survey, and that is what Ming-Fang is doing in his postdoc, and I'm sure he does a great job. And it's very difficult, you know, we have done various things to do it. So there are, you know, it's not all fun and games and happiness, but you know, from a theory point of view, it makes life easier. From a data point of view, it makes life harder. For a theorist, it makes life easier. And that is the important thing. Okay, so let's go to the notebook and make some plots. Okay, so hopefully you have all completed this. And so let us now plot some things. So what I've done here, we have a software for analyzing simulated sightlines, right? This is called Fake Spectra. We have installed it. And we have downloaded some sightlines that I prepared earlier because the full simulation volume is too large to download in a Google Drive. This software then opens the set of sightlines. So I have a set of 4,000 neutral hydrogen sightlines at redshift 3. These are selected to contain galaxies, to contain DLAs. So what we're going to do here, this is the routine for plotting a spectrum. You know, a good thing to do if you have any simulated or real data is to plot it at least once and look at it. So we're going to do that. So this, you know, in order that you have a sense of ownership, I have removed some of the arguments to this plotting routine. So the first thing we need to plot is the element of the transition, which is H for hydrogen. The second argument is the ion. This is neutral hydrogen, so 1. And the third element is the line. The transition of the Lyman alpha forest line is 1215, I think 0.6 angstroms. So this should be 1216. It is, however, 1215 because when I wrote the software, I forgot to round it. And so now we're stuck with it, and it's too late to change it. And I'm not going to change it, so haha, sorry. And then this final one, you get to pick this number. This is the sightline to plot. You can choose anything from 0 to 3,999. I encourage you to pick your favorite random number between these values. You know, maybe you can pick the date on which the day of the month in which you were born or something, so we all get slightly different sightlines, right? So I'm going to put sightline 1 because that's near the beginning, and sightline 0 did not look very attractive. So Everyone ready? Here we go. Okay, so this is a simulated Lyman alpha forest sightline. This is the neutral hydrogen absorption. There's a DLA right here. Total absorption there, bit more total absorption there, and then kind of smaller absorption lines all the way around. Let us also plot the neutral. So this is the optical depth, right, which is the integration of the neutral hydrogen along the line of sight with some extra convolutions in. This next thing we're going to plot is the neutral hydrogen density. So again, H1 and sightline 1. And I've set the limits to be from 1,800 kilometers per second either side of this feature. The sightline, the code has adjusted itself to plot the largest absorption in the middle of the plot, right? So that's why the DLA is right here. And we will see. Okay, so I'm going to have to make this a bit smaller so it all fits. There we go. Right, so hopefully you will see that I'm not lying, right? That this is a density distribution of neutral hydrogen, and there is a huge peak of neutral hydrogen density at the place where is the maximum absorption, right? So that should convince you that I haven't just made this up, that this code is kind of working. One thing that you might notice, though, is that there's absorption here and here, 500 and 1,500 kilometers per second away from this main peak. And there's kind of some hydrogen at 500, but at 1,500, there's actually nothing really, right? So that's a bit weird, right? So any guesses as to why that is? Yeah. Yeah, sorry, go ahead.
Okay, sorry. I am still lost with the first plot.
This plot?
Yeah, you're plotting velocity.
I am plotting absorption. I am plotting absorption, neutral hydrogen absorption.
Yeah.
This is in velocity space, right? Because it's a spectrum, so it gets redshifted, right? So you should imagine, this is where I miss Andrew Ponson's animation, right? So you should imagine that absorption happens from at rest frame Lyman alpha transition. That transition gets redshifted a little bit, and then absorption happens a little bit at the new Lyman alpha rest frame, and so on and so forth, right? So this is probing a set of different distances. So you can convert from velocity to position. I did this out of order now. You can convert from velocity to position. How? Well, how? Because there is a Hubble expansion rate, right? So the conversion between velocity and position is that v equals h times d, right?
But then if your peculiar velocity is of the order of 100 kilometers per second.
Oh, my goodness. You've answered the question, right? So actually,
What
that is the
question?
right answer. Okay, so the reason, right, the reason there is, so yes, so that's the answer, right? So the reason there's absorption here, but there's no neutral hydrogen here to absorb is because there's peculiar velocities, right? So this gas here is moving at some like high velocity, I think like about 500 kilometers per second relative to this. And that's why this line gets redshifted by the peculiar velocities, right? So this is a redshift space measurement of absorption, which means that everything we are doing in the Lyman alpha forest is implicitly in redshift space, which means that redshift space distortions are completely integral to every measurement that we are making and cannot be removed, okay? So that's why this guy has absorption here and no density here, right? So you see what great physics can be obtained by simply looking at the spectra, right? You doubted me, but now you know that that's what you need to do. Okay. Any questions on that? Everyone able to plot a spectrum? Everyone get like a little good feeling in their heart that they plotted a spectrum, and even though it's not a real spectrum, it looks a bit like a real spectrum. Yes, good. And if you want to plot a different spectrum, hey, no worries. You can plot it. Oh, that one's a big one. Okay, so observed DLAs, simulated DLAs. Okay, so because we do not have, because the DLAs are saturated, we are measuring a filtered version of the matter power spectrum, right? So we're probing overdensities from objects that, that are overdense, that are nonlinear, but have not yet virialized, right? And this makes sense because this is where the cosmology is, right? Virialized objects, like yesterday, right? Virialized objects forget where they came from. So this is the secret power of the laminar forest. We're sensitive to overdensities between 10 and about 100. It also mitigates the sensitivity to galaxy physics, right? So virialized objects are saturated. This doesn't mean that we are insensitive to galaxy physics, right? So if gas is kicked out of a galaxy cluster, it has to go somewhere. That somewhere is the Lyman alpha forest, right? So it does have an effect. The statement that I'm saying is that models that match the galaxy stellar mass function at redshift 0 do not affect, all models that are competitive at redshift 0 have the same effect on the Lyman alpha forest at redshift 2 and greater, right? So the statement that I'm making is that the prior that you can place on galaxy physics from the known stuff that is going on at low redshift is enough to mean that there's no freedom in the forest that you have to marginalize over, okay? You can construct models of galaxy physics that really mess with the forest. An example is a model that completely, the AGN is so strong that it annihilates the galaxy. This is actually quite easy to do. You actually have to try hard not to do it. Completely shuts off star formation by around redshift 1, right? That model will affect the laminar forest at redshift 2 significantly. However, you will have no galaxies at redshift 0, right? So that is very strongly in tension with observations, the observations that we have that galaxies exist, right? Okay. But models that are competitive, models which meet the prior of matching a stellar mass function at redshift 0, those models all have the same Lyman alpha forest, more or less. Okay. Another thing, a reason that I can give as why this might be the case is that black holes take time to grow, right? At redshift 0, there are a lot of black holes. At redshift 2, there are significantly less black holes. So the thing that is causing the effect of AGN feedback, the thing that's really suppressing the power spectrum, are these very massive black holes that are in the low Eddington accretion mode with a mass greater than like 5 times 10 to the 8. This is the threshold which we turn on the kinetic mode feedback in the Astra simulation. And I have checked that in our Lyman alpha forest simulations, that I'll get to later, we have 3 simulations that I looked at. There were 0, 1, and 16 black holes in this whole box, right? 16 black holes in 120 megaparsecs is not a lot of black holes, right? The total volume filling factor of these black holes is relatively small, right? So this does not have a big effect on the forest just because there aren't enough of them. Okay? I can't remember who asked about the Mariana physics yesterday. I can't remember, but I hope that that person is answered now. Yeah? You did, good, okay, well, are you good? Okay, you gave me a thumbs up, good, okay, so, right. Again, I'm not saying that it's not a problem. I'm saying that it's a problem that is under control, right? I'm saying that it's a problem that, can be managed. Okay, so to summarize, reasons for looking at the laminar forest. So if I may compare neutral hydrogen to galaxies, which is a kind of a silly thing to do. So galaxies, they are only in the densest regions, which are hydrogen, which are halos. Hydrogen is everywhere, so I guess that's an advantage for hydrogen. Galaxies have a significant advantage that they are intrinsically luminous. Hydrogen is not, so you have to make sure there's a backlight behind it. From a theorist's perspective, galaxies have the disadvantage that modeling them requires somehow understanding gravity, hydrodynamics, cooling, star formation, supernova, tons of things, a lot of complicated things. For hydrogen, we need to understand gravity, mostly. We need to understand hydrodynamics, how gas pressure works, and we need to understand how gas cools and how gas ionizes. And that is mostly it. And all of those things are not simple things. They need to be simulated, but they're things that we understand, right? Like hydrogen, the atomic physics of hydrogen is something that we are confident we mostly know about, right? I'm almost at the break. Yeah, let me do this before the break. So we have seen that we measure a filtered matter power spectrum on small scales, the smallest currently accessible scales, and we measure it in velocity space. Because this is kind of astronomy, we will not pass by an opportunity to have weird and unhelpful units. These weird and unhelpful units are the velocity space Fourier transformed units, right? So because we are in velocity space, we measure distances along sightlines in kilometers per second, right? We Fourier transform that, and so the units are seconds per kilometers. How do we convert from seconds to kilometers to inverse megaparsecs? We use the Hubble expansion rate, right? So V equals h times d. H is in units of kilometers per second per megaparsec. So you take 1 inverse megaparsec, divide it by h of z, and you get seconds per kilometer, right? The Lyman alpha forest is measured in units of seconds per kilometer. We, as theorists, are interested in h or over megaparsec or 1 over megaparsecs, and the conversion factor is about 100. To make life more complicated for us, this is h of z, and the redshift range is between 2 and 4. So your conversion to megaparsecs is slightly redshift dependent, right? You are probing slightly smaller scales at higher redshift and slightly larger scales at lower redshift, right? Because of the evolution of the Hubble function. This is the conversion factor. So the largest scale measured by the forest is like k of 10 to the minus 3 seconds per kilometer, which is about 0.1 h per megaparsec. Or the smallest scale measured by the EBOS or DESI Lyman alpha forest experiment is 0.02 seconds per kilometer. Actually, that's EBOS, which is about 4 h per megaparsec. This is the smallest scale measured by the Lyman alpha forest. So there are twiddles here because of the redshift dependence. You know, I'm sorry, because everything will be easier for everyone if we just use megaparsec units. But we're not going to do that because it makes the analysis much more complicated. Okay, so this is one of the many weird units that you have to deal with if you are going to be doing anything in the sky. Okay, sorry. I think it's, yeah, let me stop there for a 10-minute break. On that note, I'll see you in 10 minutes.
Computer relaxation. Are you talking about